In this video, we'll go over the Gauss elimination algorithm for solving a system of linear equations. After studying this video, you should be able to describe the steps involved in Gauss elimination in a standardized way suitable for implementation in a computer algorithm. Also, you should be able to use Gauss elimination to solve a linear system of equations by hand. You may already know how to do this if you've taken linear algebra, or also because this technique is usually taught in high school algebra courses and college algebra courses. Lastly, you should be able to employ partial pivoting to avoid division by zero problems that can arise with Gauss elimination. So what is Gauss elimination? It's a direct solution method for an n by n system of linear equations. So by direct, I mean we're making no approximations to develop this method. That's in contrast to what we did with the iterative methods for root problems in the previous algorithms we looked at. The method consists of a sequential process of removing unknowns from the equations in the system using forward elimination followed by back substitution. So let's look at each of those steps. First, we'll look at the forward elimination step. So we start by writing our matrix, our linear system in matrix form, and then writing it as what we'll call an augmented matrix, where we basically just take the b vector and add it as an additional column to our coefficient matrix. Then, starting with the first row, we're going to subtract multiples of that row to eliminate the first coefficient from the rest of the rows. And as we do that, we will call the element that we're working under in the first row, that element on the diagonal, the pivot. So that'll be the pivot element. So to get an idea of how this might work, we would say take row 2 and replace that with row 2 minus A21 over A11 times row 1. And if you look, then we would have, for example, A21 minus A21 over A11 times A11, and we would get that 0. And similarly for row 3, we would get that 0. Row 3 is going to be row 3 minus A31 over A11 times row 1. As we're doing that, we will call this term the elimination factor. In other words, that's the factor we're using to make sure that that first element is eliminated, and then the prime indicates that that is these are new elements in the matrix that come from those elimination steps. Then we're going to continue the process with the second row to remove the second coefficient from rows 3 through n. So over here with our 3 by 3 example, we're now moving our pivot to position 2, 2 in the matrix, and then eliminating this second element in row 3 by writing row 3 is equal to row 3 minus A32 prime divided by A22 prime times row 2. And that'll give us this 0 in row 3. And we'll continue down. In this case, it was just 2 steps to get those 3 zeros in a 3 by 3 system, but for an n by n system, we'll continue through the pivot elements down the diagonal until we get an upper triangular matrix, which is what remains. Once we have that upper triangular matrix, we can then solve the system with back substitution. With back substitution, we will start with the last row, solve for the unknown, then substitute that value into the next highest row. To see how that works, it's helpful to actually write this matrix, the augmented matrix, back as a linear system of equations. And then we can see that we can solve for the last value of x, x3, as b3 double prime over a3 double prime. Now that we know x3, we can plug that result into our second equation. Again, it's called back substitution because we're moving backwards up the rows. And we can solve for x2 as b2 prime minus a2 3 prime times x3, which we know, all divided by a2 2. Sorry, this was a3 3. And in this case, we know x3, so we can solve for x2. And then lastly, moving to the first row, we can solve for x1 is going to be b1 minus a13 x3, which is known, minus a12, sorry, that's a12 times x2, all divided by a11. And now we've solved for x1, x2, and x3. So let's look at doing this with numbers, and we'll go through the process one more time. So we're going to use Gauss elimination to solve this system below. And what I've done is written it already as an augmented matrix with the right-hand side vector added as a fourth column. So we will start under the first element on the diagonal, the pivot element, and start by eliminating the two elements in the column under the pivot element. So if we get row 2 is equal to row 2 minus, and now we just have 1 divided by 1 times row 1. And we can write our resulting matrix over here. So the top row is unchanged, and then we're going to have row 2 is 1, minus 1 times 1 is 0. Then we have 2 minus 1 times 1 is 1. 4 minus 1 times 1 is 3. And negative 1 minus 1 times 1 is negative 2. And then we can do the third row. Row 3 is going to be equal to row 3 minus, again, the first element in row 3 is a 1 also. So 1 over 1 times row 1, and we get, again, a 0. And then 3 minus 1 times 1 is 2, and 9 minus 1 times 1 is 8, and 1 minus 1 times 1 is 0. So now we're ready to move to the next pivot element and eliminate that 2 right there. So we'll do that. Row 3 is equal to row 3 minus 2 over 1 times row 2. And so again we have 1, 1, 1, 1 across the top, 0, 1, 3, minus 2. In the second row, 0, 0, and then we have 8 minus 2 times 3 is going to be 2, and 0 minus 2 times negative 2 is going to be 4. And now we have our upper triangular matrix. Upper triangular matrix. So let's go to back substitution. And now in this case we can just say x3 is going to be equal to 4 over 2, which is 2. x2 then is equal to negative 2 minus 3 times x3 over 1, and again that x3 value is 2, so we have negative 2 minus x3 times 2, so x2 is going to be equal to negative 8, and lastly x1 is going to be 1 minus x3 minus x2 all over 1, and we have a 2 for x2, negative 8 for x3, and so x1 is equal to 1 minus negative 8, so that'd be 9 minus 2 would be 7. And so our solution vector x is equal to 7 minus 8 and 2. So let's look at another example that brings up a potential issue. So we're going to use Gauss elimination to solve the system below. And we'll start with the first pivot element, 2, and start by writing row 2 is equal to row 2 minus, and in this case it's going to be negative 1 over 2 times row 1, and we get again 2, negative 6, negative 1, negative 38, and then 0, and then 3 minus negative 1/2 times negative 6 is again 0, and we'll see that that brings up a problem in a minute here. You may see it already. And then we have 7 minus negative 1/2 times negative 1, so it's actually 6.5, and then we have negative 34 minus negative 1/2 times negative 38, so that's actually going to be a positive 19, so negative 34 minus 19 is negative 53. And then we go to the next one, and we have row 3 is equal to row 3 minus negative 8 over 2 times row 1. So again, we'll have a 0, and then we have 1 minus negative 4 times negative 6, so we have a negative 23, negative 2 minus negative 4 times negative 1 would be a negative 6, and then we have negative 20 minus negative 4 times negative 38 is negative 172. Now, as we're doing this by hand, we see like, oh, look at that. We can already solve for x3 from the second row. But computers aren't necessarily that smart, and this makes this algorithm kind of complicated, because if we go to our next pivot, we actually have a 0 pivot element, and our next elimination factor is going to be negative 23 over 0. And here we have a problem. And again, doing this by hand, no big deal, but remember, solving a 3 by 3, of course we can do by hand, but we're setting this up to solve systems, maybe 100 by 100 equations, 100 equations by 100 unknowns using a computer, and this division by 0 problem would be a big issue in that context. So let's talk about how we can address that, and we do that with the idea of pivoting. So we have potential problems with naive Gauss elimination, and the idea of a naive Gauss elimination just means we just take the equations and go for it. No modifications to the system. And what we see is as we move through Gauss elimination, if we get a coefficient along the diagonal equal to 0, as we did in that previous example, it gives us a division by 0 problem, which is a problem. The other thing is if it's close to 0, we can get potential round-off error problems. And we're going to talk more about why that happens and how round-off error occurs when we're implementing this algorithm on a computer in some future videos. We need to cover a little more background information before we can get more into that. But for the division by 0 problem and avoiding the close to 0 problem, we can address those with the idea of partial pivoting. And the basic idea here is to determine the coefficient with the largest absolute value in the column below the pivot element, and then switch the rows so that the largest element is the pivot element. So in other words, we want the largest elements on the diagonal, if we can. If we were to take the elements to the right of the pivot element and check that and switch the columns too, this would be complete pivoting. But we don't, sorry, that's for each column. If we did row pivoting as well, we would have all of the largest elements on the diagonal. But complete pivoting we don't usually do, because then we would also need to change the x vector. So let's revisit that previous example and see how that works. So again, same system of equations, but now what I've done is reorganized the equations with partial pivoting to solve the system. So I've reorganized them as I've written them into the matrix. So now the -8 becomes the first pivot element, since it's the largest element in the first column. The -6 becomes the second pivot element, since it's the largest element in the second column. And then if we go through the forward elimination steps, we see that we end up with a nice clean upper triangular matrix, and going through back substitution, we can solve for the x's. And I'd encourage you to work through this example on your own and make sure that you can reproduce these numbers. One special case for Gauss elimination is with tridiagonal systems. Notice a tridiagonal system only has elements, it's a banded matrix with elements on the diagonal and the first off diagonal on either side. And these systems actually arise quite often in analyzing electric circuits and looking at trusses and in implementation of finite difference algorithms for differential equations. All of these are areas I talked about earlier where we will commonly encounter linear systems. So again, we have 3 diagonals in a tridiagonal banded matrix, and the rest are all zeros. And the consequence for this for Gauss elimination is we can do this with much less effort and actually develop a more efficient algorithm, because we only need to eliminate one element under each pivot element. Notice we'll just have to eliminate all of the e values here. So one element per pivot instead of going all the way down the column. So just something to make note of is if we had an algorithm that could check this case, it could be much more efficient. We'll talk more about the efficiency of Gauss elimination in a future video. So just to recap this basic introduction, Gauss elimination is going to work for any linear system that is non-singular. And again, to review what non-singular means, that means it's square, and so it's an n by n square system, and the determinant of the coefficient matrix is not 0. Or another way to think about it is the matrix inverse exists. Or another way to think about it is it's all linearly independent. It's a direct solution method. We've made no approximations. Okay? Although one thing that we will see, and I mentioned earlier this idea of round-off error, it doesn't mean that it's necessarily an exact solution. So even though it's direct, and we've made no approximations, we can still have some errors in our results. And we'll talk about that also moving forward. A couple more things. Partial pivoting, we can use that to avoid division by zero problems when we have a zero or close to it on the pivot element. And lastly, we briefly mentioned how efficient algorithms can be developed for banded systems. We'll look more into this in the next few videos.